So this is Venice, and what I'm going to be talking about is all about who gets to live in that absolutely beautiful pink palace. So you can see this is a modern photo of Venice because there's a speedboat, but the buildings you can see are much older. And the person who lived in that pink palace was the Doge, actually you pronounce it Doge, or Doge, but I'll say Doge because I'll forget. And he was the ruler of Venice, and he was elected in a way that was pretty much unchanged for 500 years. So this way of governing Venice carried for 500 years. In that palace also there was the administration of the entire Venetian Empire, and also the big room, the council chamber where the election took place. I couldn't find a 13th century picture. The election design was in 1268. This one's from 1400, so it's a bit later, but it's the earliest I could find. This is about the voyages of Marco Polo from Venice. And if you look towards the top left of the picture, you can see the Pink Palace with a balcony around it from which you can view the sea. You can see the ships coming in to trade, because both the political power and the very considerable wealth of Venice was based on the fact that for a long time they monopolized the trade between Europe and Asia. You could stand on this balcony in the shade and see yourself getting richer, basically. So Venice was an oligarchy. It was run by a load of rich traders, rich merchants. And the election algorithm was a way in which they selected a ruler amongst them. So it was absolutely not a democracy. The ordinary people of Venice had no say at all. It was a way of the oligarchs, who were all in cutthroat commercial competition with each other, to find a way to have a ruler between them. They had a shared interest for Venice to be stable, peaceful, and good for commerce. So the election had lots of different rounds, and there are two different kinds of rounds. There was a lot drawing round and an election round, and each round selected the electoral college for the next round. And the very first round was a lot drawing round. You'd start with all the electors, and from them you'd select 30, and this was done by picking balls out of an urn. You can see a boy who helped with the election he was called the ballottino, and he's pouring things into the urn to be stirred. There were 30 different colored balls. There was the total number of balls was the same as the number of all the oligarchs, which was 480 in 1268. And then after they'd been stirred, they'd be put in flasks. You can see the flasks. And then election assistants would take the flasks around to all the oligarchs. You can see it took place in the council chamber, which is absolutely opulent, lavishly decorated. The decoration came a little bit later, but already in the 13th century, it was the largest room in Europe. It was very, very impressive. And then each oligarch would pick a ball out of the flask. And if it was one of the 30 that was a different color, then they were in the first electoral college. And if they weren't, then they'd leave the room, but they'd hang around because they might be called on to be in a subsequent election college. Okay, so here's the algorithm. You start with all the oligarchs. You select 30 by lot in the way that I've said. Then out of those, you select 9. Then those 9 have to choose an electoral college of 40, and everyone in that electoral college has to get a minimum of 7 approvals out of the 9. Then the 40 are reduced by lot to 12, the 12 elect 25, the 25 are reduced by lot to 9, the 9 elect 45, the 45 are reduced by a lot to 11, the 11 elect 41, and the 41 elect a Doge. So I can see Nick laughing. Yeah, it's bonkers! It is completely bananas! What on earth were they thinking of? So when I heard this, I said, what is this? I went back and I started doing some simulation of it and trying to analyze the maths behind it. And I found that it actually had some interesting properties that might actually be useful. And maybe it's not actually as bonkers as it looks. So I'll tell you about those. But first I want to say, you're probably asking, why those numbers? Okay, so firstly, why did they reduce by lot to 30 and then by lot to 9? Why not just reduce by lot to 9? Well, I think that's to do with the difficulty of mixing the balls completely randomly in the urn. It's easier to do a more random selection if you first reduce to 30 and then mix the 30 well. The approval numbers, except for the very last round, all follow the same pattern, which is really simple, which is that you have to have the approval of at least 3/4 of the college that's selecting you. That's it, that's all it is. So 3/4 of 9 is between 6 and 7, so you need 7 approvals. And remarkably, this doesn't seem to have been noted before me and Dieter Gullman looked at it. 800 years later, we noticed this. Nobody seemed to have written about it. The last number of approvals is smaller than 3/4, and that may be because they were trying to reach consensus out of a larger college. But actually there's a fascinating paper by 2 academics called Coggins and Parali that show that the minimum number of 25 approvals within an electoral college of 41 is exactly the minimum number you need in order for it to have some, for the Doge that's selected to win in one-to-one head-to-head contests against all the other candidates. It's a remarkable result. Oh, you have to make some kind of reasonable assumptions on voters' first and second preferences and the way that they choose and stuff, but it's an interesting result. There is no way that or any of the other results I'm going to show you would have been worked out at the time, because their probability theory was not advanced enough. But they might have found something out by practice. They did a lot of elections that were much simpler rules for other roles within the Venetian Republic, which used a lot and then an election, for example. And by repeatedly running these, they might have got a feel for what led to good results. Yeah, so the originally, actually, when this was first designed, the number of people in the last college was 40. But if you think about it, there's a problem with that, which is you might get a tie, or you might get a 4-way split or a 5-way split. And in fact, one election of Doges, they did get a tie, and they resolved it by tossing a ducat, which was the gold coin. And after that, they changed the number from 40 to 41. Yeah. Okay, so the first thing I want to say is about the probability of electing a Doge that is a minority choice. So one thing that you want in electoral systems is some protections for the minority groups, so that they're not completely messed around with by majorities. And in this electoral process, you could actually get somebody who had a minority of votes. So I'm assuming here just 2 factions, but in general you could have it with more factions. I'm assuming just 2 parties, basically 2 possible candidates for Doge, but you could have it with more. You can, the one that has fewer people, voters actually approving, may still win. They have a probability that's lower. The higher, the more people who like you, the more likely it is that you'll win. That's good. But there is a probability of a minority Doge, and this meant that the majority couldn't really mess around with the minority, because the minority party might win next time. Another thing is, I've shown you what happens if you truncate the election algorithm. So you just run a few of the stages, and then you stop there, and then elect the Doge from the electoral college that you now have. And as you can see, that the probability of getting a minority Doge increases, but it increases to a sort of limit as you increase the number of rounds. And when you have the full 10 rounds, you're really not getting anything extra from if you added another 2 rounds. So the number of rounds they had was a pretty good place to stop. And if you're interested in the mathematics, this is to do with the convergence of a Markov chain. I won't explain how, but it is. Okay, another thing that's rather nice is the probability of an enforced negotiation. So an enforced negotiation happens if you have an electoral college where there is no faction in the election college that has enough people in the college to get all the approval votes that was needed. So it doesn't have more than 3/4 of the election college. Because at that point, the different factions that are represented in the college have to negotiate with each other in order to who to decide to elect to the next college, right? And this happened with a probability greater than a half, as long as you have a minority faction with about 30% of the electorate, which is good. This is about the length of services. Sorry, I'm going to admit someone. Yeah. This is about the length of services of the Doges. So this election protocol, there was a simpler one before, and this one was introduced at the 44th Doge. And if you look at the length of time they served, you can see that I don't have to do any statistics, it was shorter after the introduction of this algorithm than it was before, with one exception. So there's one Doge that served for 34 years. I'll tell you about him. On average, it was only 5 years, and it was because they tended to elect Doges who were quite old. They did this for two reasons. One was Venetians thought that a politician being old was good. Age brought wisdom. But the other reason was, you can imagine, if you're going to go for a compromise candidate, if you can't get your first choice, you might be more inclined to accept somebody who is old, because there will be likely less time until the next time you got a chance to vote for someone. Okay, the one that served for 34 years. Oh, so Dieter Goldman did some experiments with one of his students that found that indeed this election algorithm has the effect of amplifying user preferences, which means it's easier to reach a compromise candidate than might be with other election methods. Okay, so the one that served 34 years. Oh dear. Oh, I can't advance my slide. Oh dear. Oh.
Try pressing escape, Miranda, and then try again.
I will. Yes. Okay. On current slide. Yes. Okay. Here he is. Francesco Foscari, and he was a beneficiary of tactical voting. So what happened was, all the people who wanted him to be Doge, they initially voted for someone who nobody else wanted as Doge, nobody else wanted, and waited until other people started voting for Francesco Foscari in order to stop this chap from getting in. And then they all simultaneously voted for Francesco Foscari, and he passed that round and eventually was elected Doge. Okay, so this is robustness. I said it was robust. Corruption was endemic in the Venetian Republic. All the oligarchs, bribery, corruption, skullduggery, political machinations of all kinds were their hobbies, right? It's what they like doing. It was said at the time that legal disputes between oligarchs generally were tried fairly because the bribes from the two sides cancelled each other out. And they did try to buy and sell votes in this election. So the cheater's edge is a measure of how susceptible an election algorithm is to voter corruption. And I won't go into the details of what it is, but it's between 0 and 1. And if it's 0, it means that if you corrupt a small number of voters, you won't get any more advantage through the algorithm than just from the voters, that just proportionally to the number of voters that you've corrupted. So if you have proportional representation, you have a cheater's edge of 0. If you have simple majority, then the cheater's edge is very close to 1. Why? Because if you have two candidates, for example, who are very, very even in their preferences, then you just have to corrupt a few people and you completely change the result of the election. Whereas with the Doge's algorithm, the more rounds you have, the susceptibility to voter corruption decreases until it reaches on the full algorithm 0.17, which is really pretty low. So this is actually pretty robust to voter corruption. Okay, so the most obvious feature of this algorithm is ridiculously complicated, and it would have taken a long time to carry out. And some people speculated that this was, Venetians just liked complicated things. If you listen to their music, it's fairly complex. Their architecture is fairly frilly. But I think it was probably to do with security theatre. Now, security theatre is a phrase that I think was invented by Bruce Schneier. It's in one of his books. By it, he means things that are done by an organisation to show that they take security seriously, but which don't in themselves actually help with security. And he talks about some things that happen at airports, for example. If you think about this election, this was a long, complex ritual. It would have taken a long time to carry out. It was participated in by all the voters, all the oligarchs aged over 30. And by participating, they demonstrated to each other and to themselves their commitment to elect a Doge who was good for Venice, or at least for the oligarchs of Venice. And also, importantly, that they would submit to the rule of the Doge, that they wouldn't try and do a coup. And they were worried because there were horrible examples from other city-states on the Italian peninsula, which had repeated civil wars between factions. They really didn't want that to happen. They also really didn't want a king, because there was also a horrible tyrant. So it was important to demonstrate that to themselves and to each other and to the public. And it was also brand building for Venice. So they could invite foreign visitors who they would want to trade with and say, look, we have this system. It ensures that Venice is stable. It involves that Venice is peaceful, and it ensures that Venice continues to be good for business. So give us your money. Okay, so after the election, there was more security theatre. There were a whole load of parties. Venetians love parties. Parties and parades, processions, more rituals. But there was security theatre outside the election period. So this is a procession that took place every year on Palm Sunday. And it's just one of 8 sheets. So this was a long, long procession. You can see from the people looking from the balcony that it was very theatrical. There was music. This is a really important part of the procession. The Doge is just off the sheet of paper. And you can see on the left, there's the ballottino. There's the little boy who helps pick the balls out of the urn. And he is the living, walking symbol of the election algorithm. And he's there being shown off. Okay. So it was very complicated. Here is a simplified algorithm, which has pretty much exactly the same results. So if you want a simpler one, here it is. And you may be able to get it even simpler. Okay, so now I'm going to talk about something completely different, which is computational neural networks and activation functions in them. So a computational neural network takes inputs, gives weights for each of the input nodes. So if you're using it for image recognition, for example, this would be the weights encoding each pixel, for example, might be. And then you do a lot of computation using hidden layers. Deep learning has multiple hidden layers. You get to output nodes and you get weights for the output nodes. And so, for example, for image recognition, there might be an output node for each possible label. And it gives you weights for those labels. And then you need to decide what to do with those weights. So one thing you might do is you might say, you will print the label that has the highest weight, because, yeah. And that's just, you take the maximum. But if you do that, it's not very robust. Because if there are 2 labels that have very similar weights, a very small change in the weight for one of them will change the label that you print. So supposing you want something that's more robust, well, you can't do it if you only deterministically print the same label, whatever you do it. But you can do this by a choice of a function which takes the weights and instead gives you probabilities. So instead of just picking one label, it will give you the probabilities for different labels. And you can choose it in such a way that a small difference in the output weights will produce a small difference in the set of probabilities that you give to each label. This is an example of this. This is actually a kind of notorious example. This is the 3D printed turtle that looks like a rifle. But if you look at towards the left of the picture, you'll see that it's actually giving you probabilities for it being a rifle, a rocking chair, or a rhinoceros. And it might also give a small probability for it being a turtle, but it's only showing the top three. Yeah. So the properties that you want the higher the weight. If you increase the weight and a weight for one label and you leave the weights for all the other labels the same, you want to increase the probability for that label. And a small change in weights should result in a small change in probabilities. Okay, so one way in which this is commonly done, particularly for classification into more than one set. So if you have more than two sets, so you have more than two possible labels, very common way that it's used is softmax, in which what you do, you take the weights, you take their exponentials, and then you normalize. And I've given you the equation, but you can ignore the equation. And this has the effect of exaggerating the difference between the different weights when you translate them into probabilities. And also has the other properties that I said you wanted. So softmax, very commonly used. There's this recent discovery, and this is where it links into what I said before, by Elias Abissab, who was a master's student of Conor Howden, that the effect of the truncated Doge election algorithm, he only looked at the truncated algorithm, he didn't look at the full version, is very similar to softmax. Turns out it's doing the same thing. So as weights, you have, for the weight of each candidate, you have the number of oligarchs who want that candidate to be Doge. And for the output of each candidate, you have the probability that the candidate wins the election. And you find you're calculating softmax. This is amazing, right? This is the 13th century Italian election algorithm that turns out to be the same thing that is being used in 21st century AI to do image recognition and lots of other things. Amazing. But if you think about it, it's not so strange because they're actually trying to do the same thing. If you increase the number of oligarchs who want to be Doge, then you want the probability that they'll be Doge to be increased. If you have a small difference in the number of oligarchs who want a particular candidates to be Doge, for example, with bribery, then you want the probabilities to only change a small amount. And you can do that because it's, yeah. And you want to exaggerate the differences between the weights when you turn them into probabilities so that it's more easy to get a compromise candidate. It's the same problem. So why were Conor and Elias interested in it? Well, they're computational neuroscientists. Well, that's what they were doing. I think Elias has now moved into something else. And if you do experiments on human beings, so you give humans a very small amount of input data from different signals and a very small number of options, and you look at how humans choose the options. Humans choose the options in a way that's pretty much exactly softmax. That's the way they translate the input into the probability of the action. Amazing. So we do it, but it's really unclear how you would implement softmax in brain circuits. Doing exponentiation in brain circuits, nobody knows an efficient way of doing it. However, the equivalent of the election round and the lot round are very easy to implement in brain circuits. There's an absolute direct translation from the two types of round in the Doge's election, and simple ways of putting together sets of neurons. So maybe our brains are doing something like this. So this is really exciting. It's really new. You can think of all sorts of experiments that you might do in order to see what suggest things that you might, to look for things that you might measure to check whether this is the case, to look at different variants of the Doge's algorithm to see what matters to make it close to softmax, and so on. This is new research. Okay, so to conclude, here are some points for discussion, and I'm looking forward to hear the panel discuss one or two of them. One is non-deterministic algorithms. The reason why you can get robustness is that the algorithm is non-deterministic. In the example I give you, you don't just pick one label, instead you say the probabilities of all the different labels. You don't pick the same Doge every time with the same number of same voting preferences. You pick different Doges each time with certain probabilities. Secondly, computer scientists have generally avoided non-deterministic algorithms because they are horrible to debug, but they give you more space to play with. And so you can do things with non-deterministic algorithms that you can't really do with deterministic algorithms. And this is one example. Secondly, if an algorithm looks insane, then maybe you should have a look at it, because clearly it was developed by somebody who thinks in a different way from you. So maybe there's something you didn't know. I have seen few algorithms that are as insane as this one, though. Thirdly, security theatre. Security theatre is generally a phrase that is pejorative. People talk about security theatre in order to boo. And obviously it's a bad thing if it's used as a substitute for things that actually improve security. But if it's used in conjunction, and I think the Republic of Venice is one example, it might actually be useful. And lastly, I'd like to advocate multidisciplinary computer science research. I think if you have a problem in computer science, you should draw inspiration from anywhere you can find it, but in particular, with computer networks. So biological networks and social networks of people or of animals behaving together in a group tend to have distributed algorithms that are very robust to certain types of attack and quite often energy efficient as well. And they are potentially really interesting sources for ideas for creating new computer algorithms with good properties. Okay, that's it. Thank you.
Amazing, Miranda. Thank you very much. We will unmute everybody so that we can show our appreciation. Chris, do you want to press the button? I don't want to press my UI because it was freezing. So maybe we could all give a round of applause for Miranda.
Thank you.
And Chris, do you want to curate the question? We've got about sort of 10 minutes for questions.
Yeah, absolutely. So, I mean, it's an obvious question, to be honest, and one that I wanted to ask as well. So, James, do you want to unmute yourself? You probably are unmuted because I just did that.
Yeah, sure. So, yeah, I was just curious about how corrupt you think the UK's election system is, or where it sits on this corruption scale you were talking about, and how you think we can improve it from your work.
The UK's election system.
Yeah.
It's really clean compared to Venice. Really clean. No, seriously, they were buying and selling their votes the whole time.
In terms of the
how would I improve? So I would. People have asked me, should we learn from this system in order to improve? Or would it be better to use the Venetian election system in the UK? And the answer is absolutely not, because only rich men had the vote. No way.
Okay. So is there any evidence that the algorithm evolved over time?
So I mentioned that the last, so it stayed fixed for pretty much fixed for almost 500 years. But I mentioned that the size of the last electoral college was originally 40 until they had a tie, and then they changed it to 41. there was also there were also some slight procedural changes. So after the oh, I've forgotten what it's called now. After the wheeze that got Francesco. Oh, sorry, my brain's gone. The chap who I said was that had a 34-year-old reign because of clever tactics by his faction.
Foscari.
Polani. Sorry.
Foscari.
Foscari. Sorry about this. After his election, they actually tweaked the rules so it was more difficult to do that. So because you couldn't see exactly who'd voted for whom, and that was also an anti-corruption measure. There was also there was one election during which they couldn't decide who to vote to the next college, and they looked out of the window and they saw a sweet old man who was an oligarch who was going to, as he went every week, to take presents to the people in the orphanage. And they said, oh, he's a lovely old man. Let's vote for him. And he eventually became Doge, and he was a terrible Doge. He was far too weak. And after that, the election rules were changed to say that the windows, the curtains of the windows should be drawn during the election. So I also mentioned that these rules were introduced. There was a simpler version first. So there was a much simpler version that was used before this complicated election, which had, I think, only 3 rounds, but it was a similar idea, but it was much shorter. Otherwise, it was pretty much the same.
It's absolutely mind-blowing. It's fantastic. So Ian Cross, do you want to ask your question?
Sure. Yeah. Can you hear me?
Yeah.
Yeah.
I was just asking about from the history. Did this spread much? Was this did other countries cotton on to this method? Was it much admired? Did it spread around from Venice? Do we see it reach any other countries, and is it still in use today? Ignoring obviously softmax.
Okay, so I don't know anyone who used the full insanely complex method, but I did come across uses in other countries of a combination of a lot followed by an election. And in particular, so it was used in some towns in the Netherlands. It was used in some towns in the Netherlands to produce magistrates.
Okay, we seem to have lost Miranda there.
Yeah, that's frozen.
We give her a second, and then
back.
Hey Miranda, we've lost you. Do you want to turn your video off? We're getting occasional audio. If you just turn your video off or rejoin, and then we'll carry on. Give it a second. But in the meantime, maybe we can actually swap onto the panel so we can introduce some other voices. So joining us, we have George Dunlop. George is a fellow at the QTech, the Quantum Technology Enterprise Centre, the University of Bristol, and co-founder of Quantum Dice, a startup providing unpredictable random numbers. And Aubrey Stearn, and Aubrey is an interim CTO working in regulated financial environments. And she's currently taking a break from work and working on some video content. So welcome, George and Aubrey.
Hi.
So
hello, I'm back.
We're back, Miranda. Hi. So we've introduced George and Aubrey, and we're going to sort of carry on with the panel, if that's okay.
Yep.
So we're talking about non-deterministic algorithms. I just wonder whether, George, in the light of your experience, you want to just reflect on the use of or increased use of non-deterministic algorithms, given that we can have different output for the same input. So presumably non-deterministic source it affects the whole algorithm?
Yes, so essentially what I've been doing the past year is we are using a quantum random number generator to essentially to make sure that the numbers you use for protocols such as this are non-deterministic. So even if you had the same setup, for example, in here, when they elected with the bulls, what I was finding it quite interesting when they drew lots by putting all the 480 bulls into a box and then put that down to, I believe it was 40 and then 9. That's deterministic in that if you set up all the bulls in the same position and then had someone draw in the same motion, the result would be the same. So what I'm experimenting with is essentially if you had the same system we use a laser source, but if you had the same position of all the photons, of all the equipment, same temperatures, you'd still get a different result. But Miranda in her original paper actually raised that because of all this security theater, but also the complexity, the targets in a certain period of the Doge's, of the Venetian Republic, the vulnerability for the election actually became bribing the lot picker for the lot rounds of the election protocol. So because this result was robust.
I don't think anyone did that. I just saw that as a vulnerability. So if any of you want to go back in time and become Doge, that's how to do it.
I'd be interested to, because the resources from that time I'm sure are pretty. I don't know how. I'd be interested to see if they were able to target that by actually bribing. They had to. In later times, they had a weird system where they went out and sourced the first boy that the person saw became outside in the courtyard, I believe, became the lot bearer.
That's
for
right.
for the college. So I found that an interesting read when I was reading up for the panel about how they chose who would draw the lots for the next electoral college.
So they're trying to reduce vulnerability by having the entropy of the actual mixing of the balls, but presumably that physicalness is very different to what you're doing, where actually you're producing something which is fully random and not pseudo random, but not in a physical way like the ball mixing.
Yes. So for example, in election protocols, what we're looking at right now, which will tie in with Aubrey in the financial sector, is in the long term, we're looking at, say, when bonds are issued for the government, or when random bonds and securities are assigned and selected, a vulnerability, and also in electoral systems, we want to we're trying to secure the keys and the sources, such as the lot drawing, from being targeted by hackers or people who would look to compromise these election systems or these security systems, which is and being a non-deterministic source and also an algorithm is important for robustness of the security of the device, as it were.
Absolutely. So you need something which is fully random, and obviously there's a long history of leader elections and elections within distributed systems, just something that computer science is very familiar with. I wonder whether Aubrey wants to reflect on that within your experience of other election or leader elections that you've seen within distributed systems.
Yeah, I mean, I'm going to go for the low-hanging fruit on this one. So I think most of our audience will probably know HashiCorp and Console, and which uses the Raft election protocol. And I think that's loosely based on Paxos, which is probably what was majority used before that. Paxos being the Greek island. Raft is reliable, replicated, redundant, and fault-tolerant. I have to write that down because I can never remember that. But essentially what happens is that you have all of these servers, and there is a leader, and it will send a heartbeat, and everyone will recognize this. And at the point where one of these servers stops getting this heartbeat, an election is triggered. And every one of these servers is seeded with a random number for, I think it's their check, or basically the amount of time it takes for them to trigger an election. And what will happen...
I think I muted. Oh, no, not, sorry.
Sorry. And what will happen is that they will basically vote for themselves in that election, and everyone else will vote for, I think, what they can currently see, either the current leader or the new server saying that I can't see anybody. And eventually, during this new term will start, and one of these servers will either become the leader, or the existing leader will be recognized, and whoever has been isolated over there will suddenly see it again, and things will carry on. And Raft contains a ton of safety mechanisms, including like who can append to the log. So the leader is the only thing that can append the log, and basically everybody else will go, and that's the only thing they send. They don't really send remote procedure calls. They only send their log appends or trigger an election. And there's a bunch of other stuff that guarantees around like what should be in the log, and the concurrency of that, and the state machine, and then who can change the state machine, the state that that's in. So there's obviously very good articles on how Raft works, but that's particularly one of them. And Paxos is obviously being the other mechanism for voting. And I think that's probably where you would see it most, when you have any sort of distributed system where there could be a network petition and something gets torn off. I think if you would apply this to modern cloud, anybody who's running on AWS or GCP or Azure has probably had at least part of their availability zones or whatnot like come undone, and something to become slightly unstuck, and send that sort of network petition thing. There is a nuance to this, which I think is called Byzantine fault tolerance, which is a situation where something appears to be both working and non-working to different components of the system. So it's quite hard to determine what has actually failed. And I think Raft isn't tolerant to that, whereas I think there is a version of Paxos that has tolerance in it, but Paxos is like a much bigger protocol with a ton of I want to say deterministic like rule sets or decision trees that figure this stuff out, whereas Raft is way simpler, but is vulnerable to that kind of failure where something is sort of seen to be working by some components but not others.
Yeah, I mean, is it the case that any system where sort of a certain level of bad actors is potentially compromised, and obviously that's something where you have to be able, is a question of trust, is it not, between, you know?
And that is an interesting point, because most of these systems sort of believe that there is trust, like just inherently there. I don't think there's like an awful lot of thought around like not trusting the things involved in those elections. So it's an interesting vector of attack, looking at you know, how vulnerable those things are to attack, and like how you might enhance your security on that.
So do you think there's any security theatre in modern computer science like Raft, or does it require complete transparency for the security of these computer science election protocols?
I think they're relatively transparent. I think like a lot of things, like they're quite far back. So like if somebody's got that far back, like you have a very serious problem. I think we build architectures that are like, if you were to go and do something, say for example on AWS with a very big distributed system, like you will probably have lots of little isolated systems, but you're probably going to have like one domain or one AZ that's publicly facing with all your public facing services, and then you'll have like your queues, your SQS queue system to go and offload messages, and the only way to get back to probably the part of your infrastructure that runs this is to jump on a queue. And so you're probably always looking to reduce the number of ways in, but like if somebody's all the way back there already, like you probably have a very, very serious problem. So yeah, I imagine it will happen.
Non-determinism might help you. Seriously, because if, I think I mentioned this in the paper, if you have a deterministic algorithm, it means that every time there's a network partition, that you'll elect the same leader, right?
So every time you have the same result or same...
Whereas if you have a non-deterministic leader election algorithm and you get a corrupt leader, at least you're okay next time there's a network partition, you have a chance of escaping.
I like the idea that if I was an evil genius, and I was trying to think of how I might apply this somewhere, of a decentralized or DApp running on maybe one of the blockchain networks that's just deployed, that randomly targets using a non-deterministic voting protocol that you can't change.
Go for it.
That might be an interesting application.
So I've actually got a question for Miranda on a very different tack, which actually James's question triggered. Because you assigned a proportional representation system has a robustness of 0, I believe, by that measure of
T to
that.
Z, yeah.
Yeah,
So
of 0 to 1.
It's perfect on,
Yeah.
perfectly robust.
And the Venetian Republic had a 0.17. Would we be able to do a measure like that for first past the post in the UK?
Yeah, so I actually gave the figure for simple majority, simple plurality, which is 0.99 with that size of election.
And so that was for simple
so
majority.
it's basically, it's very bad, because if you have 2 parties and they have almost 50% of the vote,
Yeah.
by just bribing a very few people, you change the result entirely.
So can we model that for like would we be able to make that model for, say, put it into, if we brought in the thresholds that the UK Parliament uses?
Oh right, yeah,
and,
you
and
could
made it more,
yeah,
made
sure,
it
you could
more,
do it. Yeah.
What do you call it? Not context, detailed about like into our calculations.
Yeah, I expect it to be still fairly high, but yeah, you could, and it would be not as bad as, well, yes, it would be not as bad as 0.99, I'm guessing. And in fact, proportional representation also, because you don't have exact proportions, and also because of the rule in most proportional representation systems that if you only get a small number of votes, then you don't get any representation. Then the tutor's edge is not quite 0. I'm guessing. I haven't looked at it directly. But another thing that's nice is this gives an explanation. No, something else that gives an explanation. So there's another graph in the paper that gives an explanation that suggests that first past the post will trend to 2 parties having 50% of the vote each, whereas proportional representation will trend to having lots of very, very small parties. And the Doge's election will trend to having a very wide coalition, about 3/4 of the electorate.
Wow. Because another assumption of the paper that you make when you're running your calculations was that there would be a two factions.
Yeah, that was just to make the calculations easy, because I was actually solving the equations.
Yeah.
And it just gets horrible if you try and have more than 2 parties. But you can do simulations with more. And in fact, Dieter Goldman and his student Harold South did simulations with more.
And were there any interesting results that came up from further to what we kind of went through in the 30 minutes that have come up since with doing, if you look at, say, a three-party system within 13th century Venice?
I haven't. So more research, hey.
Well, no, it would be an interesting question to see.
I think so. One thing that you might find difficult to model is exactly how the corruption would work, or the coalitions. Yeah. So one thing about having 3/4 approval is it means that, let me get this right, that 2 smaller parties can't gang up against the larger party. I think that's right, yeah.
By that threshold, so it's essentially
some robustness that keeps the advantage to the larger party, even when there are lots of different factions.
Yeah, no, so with regards to the so essentially it forced a consensus to be found, even when, and they would just, I understand,
well, it's not forced, but it made it much easier to find a consensus. Yeah. But it also enforced negotiation. So it made it much more difficult for one faction to throw its weight around, basically. And it's a way of avoiding civil war, which is what they wanted to do. Yeah.
Right, Miranda, do you think there are going to be other examples, like within sort of the history of leader elections, that we've potentially overlooked and that we could return to? Just like, you've dug out this sort of nugget. What's the likelihood of there being others?
So I don't know whether you heard when I was cut off when I started talking about the Netherlands.
Yes, yeah, we did.
So that's another example. It's a simpler version. It's more like the truncated version, and it turns out that they were using this too.
Because I like to touch on maybe the sort of the multidisciplinary nature of this research. Clearly,
right.
we're bringing together history and ancient history together with some really interesting reflections on modern computer science. So could you maybe just say something about the sort of the multidisciplinary nature of this research?
Yeah, so to answer your question a little bit indirectly, I think it's quite likely if we look, we'll find something, because as an example, I wanted to look at ways of improving BitTorrent. And so I thought, well, it's a cooperation mechanism. Let me look at animals that cooperate. And I just picked the first few that cooperate with non-kin. There was vampire bats, and there's an interesting aquatic worm. And immediately I found 3 ideas for improving BitTorrent just by looking at them. So really, it doesn't take much. Mother Nature has come up with all sorts of fantastically useful ideas, and human beings also. So it's a good place to look.
There's a question of broadening perspective then. It's kind of being open to be inspired from other places.
Oh yeah, absolutely. And I would say especially from biological systems.
Because I guess we're not saying that, we need 13th century historians on software dev teams. Kind of that.
Hey, I'm not a 13th century historian.
but yeah, so I'm sort of parodying it. But I guess there is a serious point to be made in terms.
Yeah. So I think. So a general point is you only see a problem from your own point of view, right? And if you force yourself to see it from a different point of view, or you talk to people who have a completely different perspective, you're quite likely to get new ideas. Especially if it's an related thing, how to make a network work robustly, which is what the problem was.
I think that, some traditional software development, obviously there is a collaboration between people with different skills, but typically, software, product, UX, DevOps, I guess, so that way of working is already well established. But I think here we're talking about broadening the lens even further and then taking inspiration from other disciplines.
Yeah, absolutely. So I have publications in computer science and maths, computer science and management science, computer science and theoretical biology, computer science and philosophy, computer science and sociology. I mean, all of them are useful. Yeah. And it's just a good way of seeing things from a different point of view. But I do think that the biological ones are particularly useful.
And do you think that's a strengthening trend over time?
Oh, Christopher, thank you for the thanks very much for the reference. Do I think that's I hope so. Yeah. So yeah, and all of this is just inspiration. Like, I don't really know about Italian history. I'm not a historian, and it's just a way of getting more inspiration. And I'd recommend for all of you, if there's something that you're interested in outside computer science, you'll probably be able to find a link to it somehow if you know enough about it.
Okay, great. So we're running out of time. We've only got a few minutes left. I wonder whether there are any final comments from yourself, George, or Aubrey, anything that's any reflections or anything that's sort of occurred to you during the panel.
I think in the prep for this, we had mentioned explainability and interpretability.
Oh, yeah.
And that was an interesting point. And I think we were going to mention that, like, this is convolutional neural networks or computational neural networks. I think is one of these things that lend themselves to thinking like decisioning, and especially like credit decisioning and stuff like that. And the thing that currently prevents them being used in especially regulated environments for credit decisioning is that in the US you have.
Sorry, Aubrey, just for the sake of the audience, could you just take us through explainability and interoperability as well?
Yeah. So interpretability is the ability to observe something and predict the outcome, to see how it kind of works, to be able to look at something and know what it will do. Whereas explainability is to be able to understand like the values inside, the values of each node and how it was used. And I think an example of this would be like in a convolutional neural network that is maybe built to go and look at, say, an MRI, for example, and identify cancer, that's something where you would need that explainability to be able to say, like, well, how did it understand that pixel was something that contributed to the cancer diagnosis? And that's where explainability would be quite useful. And so that specifically is quite useful when it comes to decisioning in credit records. I think this is called XML and XAI, and it's the explainability part. And it's still, I think, there is no measure for how well you're doing an explanation of your machine learning model, but I think there are suggestions on how you would do this. But the US has the Equal Credit Opportunities Act, which says that if something is to negatively affect you in terms of a decision-making process that's based on your credit record, then you have a right to understand like what happened. And for us in the European Union, it would be in GDPR. And so there is a part of that act, or part of that declaration, is that
which I hope we get to keep.
Anytime that there's an automated decision in regards to our data, that we should be able to understand that. And so right now, if you were to build a neural network that did decisioning, it's quite hard to trace through that, and especially if you're doing training and it's a network that's been built with like a massive data set and hundreds of thousands, millions of generations, like you would have to be able to trace through all of those and understand exactly why you were declined for credit and explain that. So right now, that's one of the open things with the FCA for sure in our country, that says, we recognize that this is something that's going to be useful and we can understand the application, but there are things in our legislation and regulation that are preventative to that. And so I think folks are working through that. And I think this is, as XML gets, and it's a little x capital ML, as that evolves and we reach newer depths and better levels of understanding. And I should probably mention, like, there are lots of different ways to go and do this. So I think one prevalent one, especially in convolutional neural networks, is LRP, so layer-wise relevant propagation, which means like we're going through each generation and layer of that neural network. You do a backwards pass and work your way back through it, and that ends up sort of being a map that you have to go and feed into something else, deepwise or something, and work out how that's worked. But there are lots of other ways, and some ways only apply to some types of network, and short-term and long-term memory neural networks. There are lots, and this is really not my forte. I'm a generalist, so I'm sure any of these other folks on the panel will be able to shed more light on this by miles.
Well, maybe there can be some conversations that this will trigger. We have actually run out of time, but I'm just wondering, George, whether you've got any sort of final observations before we close.
No, I think Aubrey hit on an area that I'm actually particularly interested, so which I'm going to have to continue outside of this discussion. But with regards to explainability, like this was making it the robustness of. For my thesis and I did maths and stats for my master's, and at the end I was looking at how we can make deterministic neural nets robust against perturbations in their input. So essentially to make sure that you don't get a significantly different output if you have a slightly different change in inputs. So for example,
seriously, you can do that. I would have thought that if you just, well, let's talk about it.
So for images, you just you have to do certain transformations. It's, for example, with your tortoise, it's to make sure that if it gets recognized as a tortoise, if you rotate it or you add noise to the image, you will still get a tortoise.
Okay, so
as opposed if it had given out the right, for example, if you're doing a scanner and automating scanners at airports, that you'd get a robust classification, even if there's, like, say, EMP noise or interference.
Okay, so it's against certain changes and not arbitrary changes. Okay.
But so when you talk about explainability, we had to propagate that through the network, and so that's kind of where I touched on that area. But I don't really have anything to particularly. It's an interesting area to kind of dig out. And I guess the good thing about, despite all the theatre about, to bring it back to the Venetian one, is that you can trace. Because it was over a longer period of time, I think this went on for weeks, this election, didn't it? Then they would have had a certain level of explainability there.
Yeah, I mean, that if you count the parades and the parties, definitely. but actually it might have taken less time than you thought, because if you get enough people in an early college, then you can force through the results right up to the Doge. So your subsequent stages can be quite short.
Yeah.
Okay.
Although they might have kept it long to allow for negotiations, or because they like complicated things, or for security bit.
And I'm going to have to stop you there because we are out of time, unfortunately. But that has been a fascinating discussion. I'm sure that the conversation will keep rolling. So Miranda, George, Aubrey, thank you so much for being involved tonight. Just to let people know that all of the sessions are recorded and put on the YouTube channel, so there are replays of all the content, and we'll soon be putting the MLOps stuff up as well. So if you enjoyed tonight, please do spread the word. And one last thing is, not only are we open for sponsorship for 2021, but I'd like to trail Dawn's conference, which is coming up on the 9th and 12th of October. So it's Anthropology and Technology Conference, which is looking absolutely crackling. And there's a whole host of sort of social responsibility AI speakers. And if you would like a 10% off your ticket, then we have a code down there. So Briz at 10. Do check it out online. If you just type in Anthropology and Technology Conference, it should come up. So do have a look at that. And we will be back in December. So we're taking a break in November, and we will be back for a further session in December. So thanks very much for watching today, and say goodbye. Good night.
Good night.
Bye, folks.
Good night.
Thanks,
Good night.
everyone. That was a great discussion.
Amazing.